Okay, shall I begin?
Yeah, just once more. In case. Okay, so it's a pleasure to have Praveen among us. So Praveen is a faculty member at Chennai Mathematical Institute. And Praveen has been working on several models of computations like tree automata and counter systems, vector addition systems, vector nets, and so on and so forth. And he's primarily interested in logic and automata. And today he's going to talk about type checking for pattern-based tree transformations. So yes, Praveen, please you can start. Thanks.
Thanks, Shubhasis, for the introduction and for inviting me to give this seminar. This is a joint work with my colleague Ishwarya and our joint PhD student Sahil Maskar. Okay, so this is about pattern-based tree transformation. So we have tree transformations, and I'll begin with an example of how we capture this tree transformation. So think of these arithmetic expressions. So on the left-hand side, we have TL times T1 times TR plus TL times T2 plus TR, so on up to TL times Tn plus TR. And we would like to transform this to TL times T1 plus T2 plus up to Tn times TR. Now this is a standard transformation for expressions that is used, for example, in efficient evaluation of polynomials. Right. So what we would like to do is capture these kind of transformations, and the way we do it is through patterns. Right. So the expression on the left-hand side is captured by this pattern tree below. So we have the whole thing, the whole tree is rooted with the operator plus at the top, and then we have two children, and the variable z here represents the multiplication on the left hand side by TL and the multiplication by right hand side on with TR. And this child T1 is the expression the T1 in the middle here. So by the way, can you see the highlights that I'm pointing to on my screen?
Yeah, we can.
Okay. Yeah, okay. So if you just look at this whole tree as the abstract syntax tree of an expression, then you will just get this expression modulo the fact that instead of TL times T1 times TR, you will get Z with the child T1 and so on. And similarly, on the right hand side, we have Z just at the top, and then as children, we just have this T1 plus T2 up to Tn. Right? And we will get back the expressions on the top if we substitute the Z's here in the pattern with this context. Right? Context is nothing but a tree where leaves can have holes where you can fit in other children. So here you have this box here which is intended to carry other children when you actually substitute this into trees. So you take this context, for example, and put it in place of the Z here. What you'll get is TL, T1, TR. In place of that, you'll get a node with multiplication, and then you'll have three children, TL on the left, T1 in the center, and TR on the right. Right. So if you make this substitution uniformly throughout both the patterns, what you'll get are these trees, which are exactly the abstract syntax trees for this expression. So is it clear what I have showed so far?
Yes.
Okay. So now we'll move on to how we represent these patterns. Okay, so for this we use a formalism in trees called bimorphisms. Actually, it's not just for trees; even for words, it's there. It just happens that bimorphisms are convenient in this case. So what we do is just take these two patterns, right? The original two patterns that we had here. We just take those two and just take the pair of these. Right, we call this the source pattern on the left hand side, and we call it the target pattern on the right hand side. And it turns out that both of these patterns can be generated by applying tree homomorphisms to a single seed tree. Right, suppose you have the seed tree S like this. You have a root at the top, and then you have O plus with two children T1, and then another O plus with another two children, and so on up to Tn. and you can apply tree homomorphism. I have depicted here as a phi source, and you will get the left hand target pattern, and you apply another tree homomorphism phi target to the same seed tree, and you'll get the target pattern.
Yeah, Praveen, what is the tree in the middle? Like, so what is the one in the middle? Like, so you have something in the middle, then you were saying that you have a homomorphism.
The one in the middle is we call it the seed tree.
Seed tree, okay.
Yeah, and we apply two homomorphisms to the seed tree. One we call as phi source, so that we get the source pattern, and we apply the homomorphism phi target to the seed tree, and we get the target pattern. So the homomorphism itself I have depicted here at the bottom. I'm not given the full details, but these two should be enough. Right? So you have R of u at the center. The phi source will take it to epsilon of u, means you just drop the root and just continue applying the homomorphism to the one single child that you have for the root. On the target side, you put z at the top and then continue applying homomorphism to the single child.
So yeah. The middle tree problem, like if I understand the problem, like you want to have to do a transformation from the source tree to the target tree, right? And that is your objective, like the problem that you are or you are trying to. So you are given a source tree, and then you want to have like a transformation to the target tree from the source tree.
Our primary target is to represent these transformations. So this is just like a binary relation on a set of trees, a transduction, tree transduction.
Okay, so here the assumption is that like you are given that the tree which is there in the middle, and then you are representing these transformations.
No, the assumption is that so somehow we would like to have infinitely many pairs of the source target patterns.
Okay.
Right? Because this T1, T2, Tn, they could themselves be any arbitrary arithmetic expressions. No? So they are not coming from a finite set. So they could be arbitrary expressions. So we have these infinitely many pairs of source pattern, target pattern pairs.
Okay.
So the goal here in this slide, the secondary goal here in this slide is to somehow represent this infinitely many pairs in a finitary manner.
Okay.
And for that, we are using this bimorphism.
Mm-hmm.
Right. So we begin by saying that, okay, we have the single seed tree in the middle, and we get the source pattern and the target pattern by applying the two morphisms.
Wait, so what is the definition of a tree homomorphism? I don't know that.
Definition of a tree?
Tree homomorphism. What is the set of transformations you are allowed?
So the definition of tree homomorphism.
Definition of tree homomorphism. Okay. So quickly, I will can just say that so trees themselves basically an arrangement of letters from a fixed alphabet. Right. For example, here you have R, which is of arity 1. So it is allowed to have one child. And then we have this O plus, which is of arity 2. So it is allowed to have two children. Here I have 2, 1 and another children labeled by another O plus.
Okay.
Right, and so on. Then finally you have this Tn, which is itself a tree, which could itself be an arbitrary tree. And then you have this 0, which is a letter of arity 0. So it's not allowed to have any more children. That's it. So roughly that is a tree, and a tree homomorphism is represented like this, right? So, so one of the homomorphisms here is phi source, and it is given by rules, just like you have rules for context-free grammars, right? So you have similar rules here, and this rule here says that if you have root R and it has a single child U, then the homomorphism takes it to another tree where you get rid of the root, represented here by epsilon, and then you continue applying the homomorphism to the single child U.
Okay.
Okay, and on the other hand, if you have this O plus in the central tree with two children U, V, then this phi source homomorphism will take it to a tree which is labeled with the plus at the root, and then it will have two children. On the left side, you will have Z of U, and on the right side, it will be V. By Z of U, I mean a tree itself where the root is Z, and then you'll have one single child U.
Okay. Okay, I follow.
Right, so that is the source homomorphism, and the target homomorphism is similar. Just that here, just to get this particular pattern on the right hand side, we have said that R of U will become Z of U, right? And then O plus of U comma V will become plus U comma. And if you see that if you recursively apply these rules to the central seed tree, then the source homomorphism will give you the left hand tree, and the target homomorphism will give you the right hand tree. Yeah.
Is there a difference between writing the children in square brackets versus writing them in round brackets?
Sir, can you repeat the question? I couldn't hear.
For the Z variable, you write the children in square brackets. For the plus variable, you write them in round brackets. Is there a difference, or is it just equivalent?
No, they're just equivalent. This is basically a result of a LaTeX package that we're using to write this. So sometimes it uses a square bracket, so it's just remained as square bracket. But actually, it should be round brackets. But yeah.
Okay.
Okay. Any more questions, or can I move to the next slide?
Yeah, we can proceed.
Yeah. Okay. Okay, so with the examples that I have just shown, here are the formal definition. We call an atomic action A this triple: source pattern, target pattern, and guard. Okay, so source pattern and target pattern are just trees over some finite alphabet sigma union some set of variables. Right, so these are just like the trees that we have seen here. These two trees, right? The left hand side is the source pattern and the right hand side is the target pattern, which are just special trees where you can have the variables like Z here. Okay, and then we have this guard G, which is actually a function from the set of variables to tree automata over this finite alphabet sigma. So we have this guard function to ensure that the variables that are being substituted are substituted only with some sensible trees. For here, for example, we want to substitute Z with some term like this, where there is a hole in the center and there is a left term and there is a right term. Right? We don't want to substitute with some arbitrary subtree, which is having an operator which doesn't distribute over the other operators used. Right? So we want to have some control over what kind of trees are being substituted for the variables here, and that is the job of the guard function here. Right? So every variable is associated with an automata over the finite alphabet sigma. And this is the semantics of this atomic action. We say that the effect of an atomic action on a tree T is, we denote it by A of T. This is a set of all trees T prime such that there is a substitution sigma such that sigma of Z belongs to the guard language of Z for every variable Z. And applying this substitution sigma to the source pattern gives you the original tree T, and then applying the same substitution sigma to the target pattern gives you the tree T prime. Right? So it's just going back to the example here. This is the substitution sigma of Z. Applying it to the source pattern on the left hand side will give you the left hand tree, and then applying the same substitution to the right hand pattern will give you the right tree. So the left hand tree here is T and the right one is T prime. Okay, so the collection of all such T primes that you can obtain this way is what we call the effect of this atomic action on this tree T.
So what is the use of that guard function? Could you say that again? Like this variable to automata over?
Okay, so let me go back to the example here. Suppose we did not have any guard language and we said Z can be substituted by any tree whatsoever. Then, for example, somebody might come and say, okay, I want to substitute it with let's say a term which is having division at its root. But then division, maybe not division, maybe some XOR, for example, which doesn't distribute over the usual addition. Right? Then this transformation is something that you don't want to happen. Right? You want it to happen only with operators which allow distribution over addition. Right? So you want to control what kind of operators are used in the tree that is being substituted here. So you want to have some control over what kind of trees are being substituted for the variables. Right? And so that that control is given to us by this guard language. So for every variable z, we associate a tree automaton, and then we say that any substitution sigma that you use must be such that the sigma of z must belong to the regular language g of z.
Okay.
And that is the guard. That is the role of the guard. And in fact, you can just set it to sigma star, and then you can do any arbitrary substitution. But in practice, when you want to actually use it for some real purpose, usually it turns out that you will need to have some sensible regular language which will restrict the choices. Right, so this is the semantics of an atomic atom. So is it clear so far?
So this automata over sigma, you mean like it's a regular tree language?
Yeah, it's a regular tree language, yeah.
But the way, at least in that example that you had, like you had one particular z, and corresponding to that z, you had just one tree, right? I mean, it was not like for a, I mean, it was not a language of trees or a set of trees. I mean, you just had one specific tree for that.
So in the example, what I said is sigma of z is this particular tree.
Yes.
So I can very well take some other substitution sigma prime and associate some other similar tree with z. So it could be some TL prime and TR prime.
Okay, but
just that sigma prime of z should also come from the same guard language G of z.
Yeah, but what I'm saying is that like for a particular variable, you can replace it with just one specific tree, right? I mean the substitution.
Specific tree, yeah. For one application of your action, you can replace it with just one specific tree.
Yeah. Okay.
Okay. So I think what you mean is that this substitution must be uniform throughout the pattern. So it must be the same tree which must substitute for all the occurrences of the variable.
Yeah.
Pattern, as well as the target pattern.
Unique substitution, yes. Unique substitution and uniformly throughout this.
Uniformly throughout both the patterns, yeah. So by this question, I'm guessing that you're already kind of seeing ahead of me and guessing that because of this requirement of uniformity of the substitution, the domain of our transformations will not be a regular language. So we'll come to that.
I don't see that yet, but maybe I can. Yeah.
Okay. Fine. So now, so that was an atomic action. Now we call an action this 4 tuple S comma phi source comma phi target comma G. Now what are these? S itself is a regular tree language which we call the seed language. So this is the language from where the seed patterns, the seed trees come from. The central tree here, right, with the R and O plus. So the seed tree here comes from the seed language S. Right, and then these phi source and phi target are tree homomorphisms, like said before, and G is the guard language, guard function, like I had mentioned before. And now for every seed tree S from the seed language, there is an action AS, which is this triple, like we have here. We get the source pattern by applying the homomorphism phi source to S, the seed tree. We get the target pattern by applying the homomorphism phi target to the seed tree S. And then we retain this guard function G. Now this triple gives rise to an atomic action like we had seen before. And then finally, the semantics of an action is that suppose you have a source tree T, the effect of our action A on this tree T is the union over all seed trees in the seed languages, then we collect the effects of the individual seed actions. So that's the action of, that's the effect of an action A on the source tree.
Mhm.
Yeah, okay, is it clear? So, I mean, informally, we are just collecting all the source pattern, target pattern pairs that we are able to get from the seed languages. And then we compute the individual atomic actions that are defined. Then we collect the actions, we collect the effect of all the atomic actions.
So AT is a language of, I mean, AT is like it's a set of such tuples, right?
Yeah, it's a set of trees basically.
Yeah, sure.
It's a set of trees T prime like this.
Yeah, yeah, okay, right, yes.
Yeah. Okay. So in particular, if you kind of if you treat this, if you substitute this, no, sorry, not substitute. If you set these phi source and phi targets, the homomorphism, to the identity morphisms, then this action is basically just the transaction that you are using in the underlying formalism. That's the bimorphism. And by the way, the bimorphism here is known to be is known to capture, for example, many tree transducers, bottom-up tree transducers, top-down tree transducers, and MSO definable transducers also. So this bimorphism is just one way of representing classical tree transductions. And here what we are doing is on top of it, we are adding variables from the variables on the the seed language, and then we are getting a formalism. We are getting a more expressive formalism out of it. Right. So in particular, if you set this phi source and phi target to be the identity morphism, then this whole action is nothing but just the transduction represented by the bimorphism, phi source and phi target. Yeah. Okay. So this is our model, and so we study decision questions, decision problems about this model, and it's known that equivalence is already undecidable for bimorphisms over strings itself, and it's not very difficult to extend this result to trees. And then we have this matching problem, which is, does a given tree match a given pattern? Right, so you let's say, so going back to this example, the very first example that I had. Right, so you have this source pattern here on the left hand side, and then you have the source tree here on the left hand side. Is it even possible to match this source tree with the source pattern? Or in other words, is there a substitution sigma which when applied to the pattern here will give rise to your source tree? And that's the question. That's the matching problem. Does a given tree match a given pattern? But then we have this guard function, right? So we also want to restrict the kind of substitutions that you use. So we want to really check if there is a match between the tree given and the pattern given, respecting the given guard function.
So Praveen, just to make sure that I'm following you. So when you talk about the matching question, so it is about finding the existence of a substitution, right, and which satisfies the guard function.
Correct. Yeah. So we want to check if there exists the substitution sigma such that sigma of S, sigma of Z belongs to this guard of Z for every variable Z.
Okay.
Such that applying this substitution sigma to the pattern will give you the input tree. So this is the question. And so again, like Shivasi seems to always be one step ahead of me. So he said that this is basically about guessing the existence of substitution. And probably you have already guessed that this is NP-complete problem. Right? You just guess the existence of a substitution, and this is known to be NP-complete already for words, and it's not very difficult to extend this to our models on trees. And so this is the matching problem. And then we come to our central result, which is the type checking problem. Right, so here the question is, does there exist a seed tree S in a given seed language L of A such that applying the resulting atomic action AS on trees from L of B1. Okay, so B1 is some given automata. Applying the atomic action AS on L of B1, will it result in some tree in another language L of B2? And B1 and B2 are two automata given as input to this type checking problem. And this is the question. So intuitively, it is asking whether there exists some source tree in the first language L of B1, such that when you apply the transformation on that source tree, the resulting target tree will be in this language L of B2. Right, so this is the type checking problem, and we show that it is decidable. But before getting into the details of this, let me show some motivation for why we are tackling this type checking problem. Right, so suppose going back to our running example, suppose that on source trees, the alternation between multiplication and addition is, let's say, bounded by a constant. Right, suppose you are always applying this transformation on trees which satisfy this property, that the alternation between multiplication and addition is bounded by some constant. And now you want to check that after applying the transformation, this property is preserved.
So what do you mean by the alternation is bounded by a constant?
So this is just like alternation between quantifiers in first logic or similar formalism. So you just look at the the abstract syntax tree of your expression, and from any path along any path from the root to any leaf, you look at how many times the operator changes from plus to dot and vice versa. So every time it changes from plus to dot, there is one alternation. And suppose your input trees have the property that the maximum alternation is bounded by some constant. Let's say 2, for example, if you are looking at some expressions in some normal form, then you won't have too many alternations in your expression.
Okay. Yeah.
Suppose you have a polynomial written out as a sum of monomials, then your alternation depth is just 1.
Okay.
Right, so that is the alternation that I'm talking about. And now suppose you want to check that applying the transformation that we have to such trees should not violate the property of having constant alternation depth. Right, so this is what you want to check. And it turns out that this can be reduced to the type checking problem. Right, all you have to do is check this, set this B1 and B2 appropriately. Right, in this case, you can set B1, you can set L of B1 to be the regular language of trees with alternation bounded by some constant. And then L of B2 to the complement language. Right, now L of B2 will have trees which will have all sorts of trees with unbounded alternation depth and so on. And then if you give these as input to your type checking problem, then you will know whether this property is being violated. Right, so that is one example. Then you have another example here. Let's say that your source trees satisfy the following property. Right, you look at any subtree of your source tree which is made up of only addition operators, and suppose that such subtrees have bounded height. Right, what do I mean by this? Let me go back to the example. Right, so here you have the source tree, right? Well, this particular example does not have the property, but look at subtrees which are made up of only addition operators. Right here, for example, you have this subtree, TLT to TR. And then you have this subtree TLT and TR. So all these subtrees, suppose they have the property that they have bounded height. Okay, but when you apply this transformation, you get this subtree, right? The T1 plus T2 plus up to so on up to Tn. So this is a subtree which is made up of only addition, but now it has unbounded height. So this particular transformation, the example that we have right here, does not satisfy this property. Right. So even though on the source side, all the subtrees made up of only addition operators have bounded height, the target trees that you get does not have that property. Right. So again, you can check this by reducing it to the type checking problem by setting appropriately L of V1 and L of V2. Right. Is this clear? These two examples.
Yes.
Okay. So this is the motivation for studying the type checking problem, and we show that for our model the type checking problem is decidable.
So in general, when we talk about tree transformations, do they find applications in type checking of, say, I mean, these languages which have like typed languages and similar things? Like, so if you talk about, say, for example, functional programming languages, I mean, where or some languages which are strongly typed. So
so you're talking about the type system for lambda calculus and this.
Yeah,
Right,
is
okay.
there a kind of a broader sort of motivation behind studying tree transformations in general?
No, so the type checking problem that I mentioned is not really doesn't really have any that kind of a fundamental connection with the type systems there. It just so happens that both of them share this name type, but that's about it. There is no intended connection between these two. There might be some unintended connections in some context, but they're not intended to come from some underlying same abstraction or anything like that. These are, I mean, in general, these two are just independent problems.
Okay.
Okay. So now let me try to give an overview of how we prove the decidability of the type checking problem. So the overall idea is, so here in the diagram on the left hand side, we have the seed tree rooted at gamma, and it has two children, U1 and U2. And suppose you apply the homomorphism phi source, and this is what you get. So you get some, tree which might be using variable z, and then it says, okay, there are three children. The middle children is the first child of the C tree, and the left hand child and the right hand child, U2, both of them are copies of the right hand child of the C tree. Okay, suppose this is the action of the homomorphism on the C tree. Now, for the type checking problem, we are supposed to check that the source tree is actually in this language of V1. So what we would like to do is kind of run this automaton V1 on this resulting tree. Right, so the overall idea is to use this kind of standard results in automata theory, which says that usually automata are closed under inverse homomorphisms. Right, so you want to run an automata on this tree, which is actually the result of applying a homomorphism on this tree. So we would like to run an automaton on the seed tree, which simulates running V1 on the homomorphic image. Right. So is the overall idea kind of clear?
Yeah.
Right. So that is the overall approach that we would like to take. But at a conceptual level, I mean, a lot of details have to be worked out, but at the conceptual level, there are mainly two problems. The first one is the presence of these variables z. Right. So these can be substituted by any tree from an infinite set. So we have this God function g, right? So this g of z will give you a regular language of trees, and z can be substituted by potentially any of those trees. Right? And that set of trees is infinite. So we don't know exactly where it is going to, what exactly that tree is going to be. Right? So that is one problem. And the second problem is that children can be repeated multiple times in the transform tree. Right? So here, for example, you have 2 copies of U2 in the homomorphic image. Right? And this I'm talking in general for a nonlinear homomorphism. So for various purposes, people have studied restrictions of homomorphisms where you don't allow this repetitions. For example, you restrict yourself to linear morphisms. But in general, if you allow unrestricted morphisms, then you can have this problem also. Right. So these two are the main conceptual obstacles that we need to overcome in order to apply this closed under inverse morphism idea. So now how do we tackle these problems? Okay. So first let's try to tackle the first problem. We have to somehow abstract this infinitely many trees. So for this again we use this classical idea from automata theory. Suppose you have a string W. Yes, I will illustrate with strings so that it becomes simpler to understand. Suppose you have the string W and you have an automaton running on the string, and the automaton starts at some start state and it reads the string and ends at the end state. You collect all such pairs P comma Q such that the automaton can start from P, read W and end at Q. You collect all such pairs and we call the set of such pairs the extended transition relation of W. This is just like extending the transition function from individual letters to strings. An individual letter, you say if you are in state Q and you read a letter A, you can go to Q prime. Here, similarly, here we are saying that you are in state P, you read this string W, then you can end up in state Q. So you collect all such pairs P comma Q and call it the extended transition relation of W. And this is a standard idea from automata theory, and this is where the idea for algebraic automata theory starts. But what we do is kind of take this concept and apply it to trees, or in particular contexts, which are nothing but trees with holes like this. Right, so here you do the same thing. You collect all k plus 1 tuples, p1 to pk comma q, such that your automaton b1 can start from p1 to pk, the bottom, and can end up at q, at the top, the root. Right, and we call this the extended transition relation for this context tau. Okay, so once we do this, since we are working with finite state automata, then it's very easy to conclude that there are only finitely many possible extended transition relations. Because after all, they are just k plus 1 tuples of elements from a finite set, so there are only finitely many possibilities of this extended transition relation, even though the context tau itself might come from an infinite set. Right, so this is how we take this infinite set of contexts and abstract it with a finite set. Right. So at this stage, I hope there's at least vaguely you kind of see how we overcome this problem of infinitely many contexts. So a little later, I will tell you exactly how this is fitting into the actual decision procedure. But at least is this idea of extended transition relation clear?
Yeah.
Right. Okay. So what we do with this idea is that so we go back to this idea of running an automaton on the seed tree, trying to simulate the running of automaton B1 on the homomorphic image. But instead of having variables like this, which are supposed to be substituted, we treat this variable Z like a letter, a parity K, right? And set its transition relation delta of Z to some extended transition relation of some context tau. Now, which context do we take? We cannot decide that a priori. So what we do is just use brute force and try exhaustively with all possibilities. And so just like we have seen in the previous slide, this will come from only a finite set. Although it's a huge number, there could be exponentially many possibilities here for this extended transition relation, but at least we get a decision procedure. Right? So this is the strategy for overcoming problem 1. Okay, now what about problem 2? Here the problem is that a single child here like U2 in the seed tree. Yeah.
So Praveen, what was K in the previous slide? So you had you tried with some anti-K.
K is here the number of holes that you can have in the context, which substitutes for Z.
Okay.
So in our running example, we had this TL, box, and TR, right? The box was one hole. So K is the K plus 1. No, K is the number of holes. Yeah. So because you can plug in any tree to that hole, right? And when you finally run your automaton B1, the tree that you have hooked to that hole can come with any state.
Okay.
And then you see what is the effect of continuing the automaton and what will be the effect at its root. So that's the idea. So now coming to problem 2, you have this U2, the right child here in the seed language, and it is copied twice on the target side in the homomorphic image. Now, how do you tackle this? For example, suppose you are trying to run your automaton B1 on this homomorphic image, and B1 says that suppose this left child is ended at Q1 and the right child is ended at Q3, then B1 says I can end up with Q at the root. But now in the seed language, in the seed tree, how do you ensure that this child U2 satisfies these two conditions? Here we have two conditions on U2. First, it must end at Q1. It must also end at Q3. Right? So this is what we would like to do to the seed tree. Yeah. And I had written this picture hoping that by the time you see this picture, you would have already guessed how we solve this problem. And we solve it by using an alternating tree automaton. And we just say, okay, we start at the root here with Q, and then to the right child, we send two copies, one in state Q1 and one in state Q3. And we would like both of these copies to end in a successful run. Okay, so that's how we solve the second problem. Okay, so putting these two, all these ideas together, see here is an overview of the overall decision procedure. Given an instance of the type checking problem, we design an alternating tree automaton, which is designed to run on a seed tree S, simulating B1 on the homomorphic image by source of S, and running B2 on the homomorphic image by target of S. Right, so it is simulating two automaton at the same time. Right? So this is the overall function of the tree automaton. And then every variable Z is treated like a letter of appropriatority, whose transition relation is set to some extended transition relation tau Z for some arbitrarily chosen tau Z. So now the type checking problem is equivalent to non-emptiness of the language accepted by this alternating automaton for some choice of context tau Z for every variable Z. Right? So as I have already said, the choice of this tau Z is arbitrary. So we have to kind of exhaust all the possibilities of the extended transition relations. Right? So basically then we get a decision procedure by checking the non-emptiness exhaustively for every possible choice of them. So this is the overall idea of our decision procedure. Okay, so that's it. So just to conclude, we currently don't know the exact complexity of the type checking problem. For the current decision procedure that we have, we get some run expression with the double exponential time as the first case running time, but
Right?
we don't have.
Could you just go back to the previous slide? So the decidability, I mean, here, for example, like, so when you say every possible choice of contexts, so here you get those finitely many relations, right? I mean,
Yeah.
and that sort of bounds kind of, I mean, how much you have to explore. Like after some time, you will see that it's kind of repeating, so you don't have to,
Yeah.
right? I mean, so these tuples that you were saying. So since you were talking about finite state automata, so essentially those tuples that you will have is like the number of relations that you will have is finite.
Yeah, correct.
Uh, so counting how many relations that you will have doesn't help you in getting the complexity. Like
No, we do get an upper bound. So in fact, I mean, in the paper we have, we give an expression with roughly some double exponential running time, which is basically coming from counting this number of possible relations, I just said. So
right.
basically, we just want to, I mean, the crude upper bound is the number of possible k plus one array relations on a set Q.
Yeah.
Right, which is you can have, I mean, you can have mod Q to the k plus one total number of tuples. So the number of relations is 2 to the mod Q to the mod, 2 to the mod Q to the k, which is basically a double exponential. And that is that is roughly the kind of upper bound that we get. Right? But we don't have any matching lower bound. So that's what I actually mean here. We have a crude upper bound, but currently we don't have any matching lower bound.
So what is a trivial lower bound do you have? Like something comes from strings, for example, like string transformations.
I think you can get a exponential time lower bound. So in fact, if you restrict this to the problem of just one pattern, so what I mean by this is, suppose your seed language is a singleton language, is just a language consisting of one single tree. So you just have one atomic action, and you ask this type checking problem for this one atomic action. So it turns out that you can get an exponential time lower bound for that by reducing the intersection problem for tree automata. Suppose you have the n deterministic top-down tree automata, and you want to check whether their intersection is non-empty. So that is known to be exponential time complete, and we can reduce that to the type checking problem for a single atomic action. So that's the best we know currently, exponential time.
Okay.
And upper bound that we have from the current decision procedure is like a double exponential, where this arity k is at the the degree of the polynomial at the top. So there is a gap in the complexity. Okay, so another question that can actually ask is, in place of bimorphisms, what if we use other formalisms? Let's say, for example, streaming tree transducers. So what happens then? Or more abstractly, our model can be thought of as taking bimorphisms and extending their expressivity by adding variables. Right? So you can think of this whole thing as taking one kind of tree transducer formalism and extending the expressivity by adding variables. Now you can ask the question, what does this extension exactly do? So suppose you start with bimorphism, we have seen that, okay, I didn't mention this explicitly during the talk, but it's not very difficult to see that in our model, we can have transformations where the domain is not necessarily a regular language. Right? In fact, the example that I did show, you have source trees where this Z keeps on repeating. Right. So I said the sigma of Z should be a uniform transformation throughout. So you have multiple children, unboundedly many children, which are all sharing the same subtree. And only those trees are in the domain of our transformation. And the set of such trees is not a regular tree language. Right? So already our formalism is kind of incomparable to other classical transductions like bimorphisms and MSO definable transductions, simply because the domain need not be a regular language. Right? So the question that we are asking here is kind of in the abstract setting, if we think of our formalism as taking a classical tree transduction and adding variables, what effect does it do to the transduction itself? That's a kind of question that we are asking. Yeah, so this is what I had to say. If there are any questions, I will try to answer.
Questions? So this last thing about adding variables, I mean, I mean, so this I didn't fully understand. Like you already had variables in your the source tree, right? I mean, so what do you exactly mean by
No,
adding?
so what I mean is the underlying transduction that we have. So let me go back to the formal definition. Right. So we have this. If you just take these morphisms itself and say that instead of the sigma union variable, suppose you just have sigma.
Okay.
Right. So these phi source and phi target are just homomorphisms from gamma to sigma.
Right.
Then that itself is a tree transduction.
Right.
Now what we are saying is now instead of just trees over sigma, you make it trees over sigma union variables. And then we are adding one more layer in the semantic side, saying that, okay, you treat this tree on the right hand side as a pattern and try to match it with some other tree by substituting the variables.
Okay.
Right. So we take this classical bimorphism transduction, then extend it by adding variables and substitutions. So that's what I mean by adding variables. So you can think of it as you can think of this as extending the expressivity of this classical tree transduction.
Okay. Okay.
So
Nice.
the question we are asking is in an abstract setting, when you do this kind of transformation, when you do this kind of augmentation, what effect does it have? I mean, for example, you can ask questions like, is streaming tree transducers closed under this variable extension? Questions like that.
Any other questions?
Are you concerned with the size of the trees that you have?
So can you repeat the question? I did not catch the last word.
The size of the trees that you have?
The size of the trees?
Yeah.
So when you are doing the transformation, so are you also concerned with the size of the trees? So for example, you may be interested in some smaller tree or something like that.
Okay. So in general, it turns out that we are using bimorphisms. So as I already mentioned, you can also have non-linear homomorphisms, which can take a tree and produce exponentially sized trees. I mean, you can just imagine, right? You can have two copies of one single child. And if you do this recursively, if you have, a tree of depth n, and every child you're producing two copies, then the resulting tree can be exponentially sized.
So that is actually where my question is coming from, because that is a feature of, that is a consequence of the fact that you are working with trees. If you work with directed acyclic graphs, then that won't happen. You can just have parallel edges.
So then, okay, then you are talking about not tree morphisms, but in general, more about graph grammars and graph transformations.
Which transformation?
Graph transform.
Graph transformations. Yeah.
Yeah, but I only want to work with DAX.
Oh, okay. Okay, you're restricting to directed acyclic graphs. Okay, so that I mean, we don't. At least in this work, we have not looked at those kind of models.
Okay. Because I thought those won't grow that much, but it's okay.
So if you make your transformation linear, then does it help in your complexity somehow? Like will
If it is linear,
for example, MSO transactions will possibly be linear, right? Like MSO. MSO.
MSO transactions are linear, yes. But so your question is, will it give a better upper bound, for example,
Yeah.
for a decision procedure? It's possible. I don't know the answer right now. It's possible that the kind of alternating tree automaton that we get, maybe it has some special properties because it is coming from this linear transformation. So maybe there is some special way of checking non-emptiness, which might give us some better upper bounds.
I mean, you need an alternation, right? There, because you were saying that it's just one copy. So I may not need the alternation. It's just an existential kind of thing rather than not.
Yeah, but we also use alternation for other purposes. For example, we need to run both B1 and B2. Both the so we have these two automata, right? From the type checking problem, we have these two automata from the source side and also the target side. So we have to simulate both these automata.
Okay.
And also another thing that I kind of pushed under the carpet and did not explicitly mention that we also have to simulate this the seed language itself. We are running, remember, we are running this automaton on the seed tree. So the seed tree must come from the seed language, which is itself given in the form of an automaton. So that automaton itself has to be simulated. So we already have to simulate these three automata. But then on top of it, if we have a nonlinear morphisms, each child might have to be parsed with multiple copies. But in case of linear morphisms, this fourth condition doesn't come. So we only have to run these three copies, which probably we might be able to do by just taking this Cartesian product of the three automata. So that might give us a better bound in the case of linear morphisms. Yeah, it might be possible.
Okay, so if there are no more questions, let's then thank Praveen. So thank you.
Thank you for listening to my talk and inviting me.
Okay, thank you.